Hey everyone, tonight we begin with something that'll make your brain hurt in the most beautiful way possible. We're diving into one of the most mind-bending mysteries in all of physics, a puzzle so profound that it's kept the smartest people on Earth awake at night for decades. The information paradox. Do black holes actually forget? So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And let me know in the comments where you're tuning in from and what time it is for you. It's always fascinating to see who's joining us from around the world. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. Picture this. You're holding your favorite book. Every word, every comma, every coffee stain on page 47. All of that is information. Now imagine throwing that book into a black hole. Common sense tells us the book is gone forever, right? But here's where things get weird. According to the fundamental laws of physics, information can never be destroyed, ever. It can be scrambled, hidden, transformed beyond recognition, but never truly erased. So what happens when something that can never be destroyed meets something that seems to destroy everything? Welcome to the information paradox, the scientific equivalent of an unstoppable force meeting an immovable object. This isn't just some abstract thought experiment dreamed up by bored physicists. This is a crisis that strikes at the very heart of reality itself. Because if black holes can destroy information, then everything we think we know about how the universe works is wrong. The laws of quantum mechanics, the principle of conservation, the very foundations of physics, all of it crumbles. But if they can't destroy information, then where does it go? How does it escape from something that light itself can't flee from? Tonight, we're going to unpack this cosmic mystery step by step. We'll journey into the heart of a black hole, explore the strange world of Hawking radiation, and discover why some of the brightest minds in science have been losing sleep over this puzzle for over 40 years. By the end, you'll understand why this seemingly abstract question about information and black holes might hold the key to understanding the deepest secrets of our universe. But first, let's start with what we actually know about black holes. And trust me, the reality is far stranger than any science fiction movie ever imagined. When most people think of black holes, they picture cosmic vacuum cleaners, monstrous entities that suck up everything around them. But that's not quite right. Black holes don't suck. They're more like cosmic bowling balls sitting on a stretched rubber sheet, the sheet being space-time itself. The heavier the ball, the deeper the dent. And if that dent is deep enough, anything that gets too close just rolls in and can never climb back out. The point of no return is called the event horizon. Cross that invisible boundary, and you're committed to a one-way trip to the center. Not because the black hole is actively pulling you in, but because space-time itself is so warped that all paths lead inward. It's like being in a room where every door is marked exit, but they all lead deeper into the building. Now here's what makes this truly bizarre. From your perspective, falling into a black hole, nothing dramatic happens when you cross the event horizon. You don't hit a wall or feel a sudden jolt. You just keep falling, watching the universe above you stretch and distort as time itself gets weird. But from the outside, from the perspective of someone watching you fall, You appear to slow down as you approach the event horizon, your image getting redder and fainter until you fade away like a ghost. You never actually seem to cross the boundary. You just freeze there, suspended at the edge of forever. This is our first hint that black holes play by very different rules when it comes to information. Because what happened to you? Did you fall in or didn't you? The answer, disturbingly, seems to depend on who's asking. But let's say you do make it inside. What's waiting for you at the center? For decades, physicists thought they knew a singularity, a point of infinite density where the laws of physics break down completely, matter compressed to a mathematical point, space-time curved to infinity. It's the place where equations go to die, spitting out infinities instead of sensible answers. But here's the thing about infinities in physics. They're usually a sign that you're doing something wrong. They're nature's way of saying your theory isn't complete. And increasingly, many physicists suspect that singularities don't actually exist. They're mathematical artifacts, symptoms of our incomplete understanding, rather than real features of the universe. So what's really at the center of a black hole? Nobody knows for sure. Some theories suggest a firewall, a wall of energy so intense it would incinerate anything that touched it. Others propose a fuzzball, a tangled mess of strings vibrating in dimensions we can't even imagine. Still others think the center might be a wormhole, a tunnel connecting our black hole to some distant part of the universe, or even to another universe entirely. The honest truth is we have no idea what's inside a black hole, because no information can ever escape to tell us. Or at least, that's what we thought until Stephen Hawking came along and changed everything. In 1974, a young physicist named Stephen Hawking was thinking about black holes and quantum mechanics. He was trying to understand what happens near the event horizon when quantum effects are taken into account. And what he discovered shocked the physics world. According to quantum mechanics, empty space isn't actually empty. It's a seething foam of particles and antiparticles constantly popping into existence and annihilating each other. These virtual particles usually live for such a brief moment that they're gone before you can detect them. But near a black hole's event horizon, something strange happens. Sometimes, one particle from these virtual pairs falls into the black hole while its partner escapes. The escaping particle becomes real, carrying away a tiny bit of energy. And since energy and mass are equivalent, this means the black hole must lose a tiny bit of mass to compensate. The black hole is evaporating, one particle at a time. This process is called Hawking radiation, and it completely revolutionized our understanding of black holes. These cosmic monsters aren't eternal. They're slowly shrinking, bleeding energy into space, and the smaller they get, the faster they evaporate. A black hole with the mass of our sun would take longer than the age of the universe to completely evaporate. But in the far distant future, when the stars have burned out and the universe is cold and dark, even the most massive black holes will eventually disappear in a final burst of radiation. But here's where Hawking's discovery becomes deeply troubling. The radiation appears to be completely random. It carries no information about what fell into the black hole. Your book, your smartphone, your grandmother's secret recipe for apple pie, all of it reduced to the same featureless thermal radiation. It's as if the black hole has amnesia, forgetting everything that ever fell into it. And black holes evaporate. then quantum, this is where the information paradox rears its ugly head. Because if information is truly destroyed when that makes modern life possible, the eyes, chemistry, biology, and pretty much every technology mechanics is wrong. And if quantum mechanics is wrong, then so stakes couldn't be higher. We're not just talking about some obscure corner of theoretical physics. We're talking about the fundamental consistency of reality itself. Think about it this way. Every atom in your body, every thought in your head, every memory you hold dear, all of it is information. The precise arrangement of particles, the quantum states of electrons, the intricate patterns that make you uniquely you. If black holes can erase information, then in principle, they could erase you not just physically, but informationally. You wouldn't just be dead, you'd be unmade, as if you had never existed at all. But it gets worse. The information paradox doesn't just threaten our understanding of black holes, it threatens the very notion of causality itself. In a universe where information can be destroyed, effects might not have causes. The future might not depend on the past. The elegant mathematical structures that describe our universe might be nothing more than beautiful lies. This is why physicists have been losing sleep over this problem for decades. It's not just an academic puzzle, it's an existential crisis for physics itself. And the more we learn about black holes, the deeper the mystery becomes. Some physicists have proposed that the information isn't actually destroyed. Maybe it's encoded on the surface of the black hole, like a hologram projected onto the event horizon. Maybe it escapes through subtle correlations in the Hawking radiation that we haven't learned to detect yet. Maybe black holes are connected by hidden wormholes that allow information to escape through the back door. But every proposed solution creates new problems. If information is stored on the surface, how does it get there without violating relativity? If it escapes in the radiation, why does the radiation look so random? If wormholes provide an escape route, where do they lead and how do they form? The more we dig into this problem, the more we realize how little we actually understand about the fundamental nature of reality. Black holes have become laboratories for testing our deepest theories about space, time, matter, and information. And so far, they're failing every test we throw at them. But that's not necessarily a bad thing. Throughout history, the biggest breakthroughs in physics have come from contradictions and paradoxes. When our theories break down, it's usually a sign that something new and wonderful is waiting to be discovered. The information paradox might be telling us that our current understanding of physics is incomplete, that there are deeper layers of reality we haven't even imagined yet. Some physicists think the solution might require a complete rethinking of what we mean by space and time. Others believe it will demand new mathematics that doesn't even exist yet. Still others suspect that the answer lies in the strange quantum entanglements that connect particles across vast distances, creating invisible threads that weave the fabric of reality together. What's certain is that the information paradox has opened a window into the deepest mysteries of existence. It's forced us to confront fundamental questions about the nature of information, the structure of space-time, and the ultimate fate of everything in the universe. And the answers, when they come, will likely reshape our understanding of reality in ways we can't even imagine. The story gets even stranger when we dive deeper into what information actually means in the quantum world. You see, in our everyday experience, information seems pretty straightforward. This book has words, that hard drive has files, your brain has memories. But at the quantum level, information becomes something almost mystical, something that seems to exist beyond the physical objects that carry it. Consider a single electron spinning around an atomic nucleus. That electron doesn't just have a position and velocity. It has what physicists call quantum states, properties like spin, charge, and momentum that exist in a bizarre superposition until they're measured. Each electron carries information about its history, about every interaction it's ever had, about its quantum entanglement with other particles scattered across the universe. This information isn't written anywhere you can point to. It's woven into the very fabric of the electron's existence. Now multiply that by every particle in your body. Every atom in your DNA carries quantum information that's been accumulating for billions of years. The carbon in your cells was forged in the heart of a dying star. The calcium in your bones was scattered by a supernova explosion. The iron in your blood carries quantum memories of cosmic violence that happened before Earth even existed. You're not just made of matter, you're made of information with a pedigree that stretches back to the beginning of time. And here's where things quantum mechanics tells us that this get truly mind-bending. Information is eternal. It can be scrambled, hidden, encoded in ways that make it impossible to read, but it can never be erased. Never. This principle, called unitarity, is so fundamental that it's built into the very mathematics of quantum theory. Violate it, and the whole elegant structure of modern physics collapses like a house of cards. But black holes seem to mock this principle. They appear to take all that precious quantum information and simply delete it, as if the universe has a cosmic trash can that permanently destroys data. It's like having an indestructible library where books can be moved, reorganized, even shredded into confetti, but never truly destroyed. And then discovering a furnace that seems to burn books so completely that not even ashes remain. Stephen Hawking himself was deeply troubled by this paradox. In the 1970s, he argued that information really was being destroyed, that black holes were genuine exceptions to the rules of quantum mechanics. But this position became increasingly uncomfortable as physicists realized just how catastrophic such exceptions would be. If information could be destroyed anywhere, it could be destroyed everywhere. The universe would become fundamentally unpredictable, a place where cause and effect break down completely. The pressure mounted for decades. Physicists proposed solution after solution, each more exotic than the last. Maybe black holes weren't actually black. Maybe they had hidden structure that preserved information in ways we couldn't detect. Maybe Hawking radiation wasn't random after all, but carried subtle patterns that encoded everything that had ever fallen in. Maybe the very notion of inside and outside a black hole was an illusion created by our limited perspective. By the early 2000s, the weight of evidence was becoming overwhelming. Too many theoretical frameworks, from string theory to loop quantum gravity, suggested that information had to be preserved somehow. The mathematics was too elegant, too consistent across different approaches to be wrong. Something had to give, and then in 2004, Stephen Hawking did something that shocked the physics world. At a conference in Dublin, he stood up and conceded defeat. He admitted that he'd been wrong for 30 years. Information, he declared, was not destroyed by black holes after all. It was preserved in ways we didn't understand yet, encoded in the Hawking radiation through mechanisms so subtle that they'd escaped detection. But Hawking's concession, while dramatic, didn't actually solve the paradox. It just shifted the problem. If information really is preserved in Hawking radiation, then the radiation can't be the simple thermal glow that Hawking's original calculations predicted. It has to be incredibly complex, carrying encoded information about every particle that ever fell into the black hole. But how? How can random-looking thermal radiation carry detailed information about books, planets, and entire civilizations? This is where the story takes another bizarre turn. Some physicists began to suspect that the information paradox was pointing towards something even more fundamental than black holes or quantum mechanics. It was pointing toward the holographic nature of reality itself. Imagine you're looking at a hologram on a credit card. The three-dimensional image appears to have depth and substance, but all the information that creates that image is actually stored on the two-dimensional surface of the card. The entire three-dimensional reality is an illusion projected from a lower dimensional boundary. What if our universe works the same way? What if everything we think of as three-dimensional reality, all the volume and space and depth that makes up our world, is actually information encoded on a distant two-dimensional surface? This isn't just wild speculation, it's a serious theoretical framework called the holographic principle, and it's emerged from decades of careful mathematical work on black holes and quantum gravity. According to this principle, the event horizon of a black hole isn't just a boundary, it's a storage device. Every bit of information that falls into the black hole gets encoded on the surface of the horizon, like data written on the world's most exotic hard drive. From the outside, the black hole looks three-dimensional, with volume and interior structure. But all the information that defines it is actually stored in two dimensions on its surface. This would solve the information paradox in an elegant way. When a black hole evaporates, the information isn't destroyed because it was never inside the black hole to begin with. It was always on the surface, encoded in the geometry of the event horizon itself. As the black hole shrinks and eventually disappears, this surface information gets transferred to the Hawking radiation, preserving every quantum bit that ever fell in. But accepting the holographic solution creates its own set of mind-bending consequences. If black holes are holographic, then maybe everything else is too. Maybe the entire universe is information encoded on some distant boundary that we can't even perceive. Maybe the three-dimensional reality we experience every day is just a shadow, a projection of more fundamental, two-dimensional physics happening somewhere else. This isn't just philosophical speculation. Physicists have found concrete mathematical evidence for holographic behavior in certain theoretical models. They've discovered that the physics of gravity in three dimensions can be perfectly described by quantum field theory in two dimensions. It's as if the universe is running two completely different operating systems that somehow produce identical results. The implications are staggering. If reality is holographic, then everything we think we know about space, distance, and locality might be wrong. The book in your hands might not actually be in your hands, The neurons firing in your brain might not actually be in your brain. The information that defines you might be encoded on some distant surface, projected into the three-dimensional theater where you experience your life. But even the holographic solution doesn't answer every question about the information paradox. It explains how information might be preserved, but it doesn't explain how that information gets from the interior of a black hole to its surface. If you fall past the event horizon, your information somehow has to tunnel through space-time to reach the boundary. But how, and how fast? And what does this mean for your subjective experience as you fall? Some physicists have proposed even more radical solutions. What if black holes don't have interiors at all? What if the event horizon is like a one-way mirror from the inside? What, appearing solid from the outside but transparent, if the singularity at the center is replaced by something called a firewall, a wall of energy so intense that it incinerates anything approaching it? The firewall idea is particularly disturbing because it violates one of Einstein's most cherished principles. According to general relativity, crossing the event horizon should be a smooth, unremarkable experience. You shouldn't notice anything special happening. But a firewall would make the event horizon a place of violence and destruction, visible to anyone falling in. It would mean that Einstein's theory, which has passed every experimental test for over a century, breaks down at the most extreme boundaries of space-time. Other physicists have embraced even wilder possibilities. Maybe black holes are wormholes in disguise, tunnels connecting distant regions of space-time. Maybe information doesn't get destroyed or preserved, but gets transported to parallel universes through quantum mechanical tunneling. Maybe the paradox is telling us that time itself is an illusion, that past, present, and future are all equally real, and information can flow backward as easily as forward. Each proposed solution opens new doors to understanding, but also new rooms full of questions. The more we learn about black holes, the more we realize how much we don't know about the fundamental structure of reality. These cosmic monsters have become laboratories for testing our deepest theories, and they keep revealing cracks in our understanding that we never knew existed. What's perhaps most remarkable is how this seemingly abstract problem connects to practical questions about computation, memory, and consciousness. If information really is indestructible, then every thought you've ever had, every decision you've ever made, every moment of your existence is still out there somewhere, encoded in the quantum foam of space-time. The universe might be the ultimate backup drive, preserving every bit of information that's ever existed in forms we're only beginning to understand. But this raises profound questions about identity and continuity. If your information is scattered across the cosmos, encoded in black hole horizons and Hawking radiation and quantum entanglements, then what makes you uniquely you? Are you the pattern of information, or are you the physical substrate that carries it? If that information could be reconstructed somewhere else, would the result be you or just a copy? These aren't just philosophical puzzles anymore. As we develop more sophisticated theories of quantum gravity and more powerful ways to study black holes, we're edging closer to experimental tests that might finally resolve the information paradox. The Laser Interferometer Gravitational Wave Observatory has already detected ripples in space-time, from colliding black holes. Future generations of gravitational wave detectors might be sensitive enough to detect the subtle signatures of information preservation in Hawking radiation. Quantum computers, still in their infancy, are beginning to simulate black hole physics in laboratory settings. These machines can model the evolution of quantum information in ways that might reveal whether the paradox is real or just a limitation of our current mathematical tools. If we can create artificial black holes in quantum simulators, we might finally answer whether information truly disappears or whether it's preserved through mechanisms too subtle for us to detect. But here's where the story takes yet another twist that might make your head spin. Some physicists are now questioning whether the information paradox is even the right question to ask. What if we're approaching this whole problem backward? What if instead of asking whether black holes destroy information, we should be asking what information actually means in a universe where space and time themselves might be emergent properties? So we can consider this possibility. What if space-time isn't fundamental at all, but rather something that emerges from more basic ingredients, like temperature emerging from the motion of molecules? In this view, the familiar three-dimensional world we inhabit would be like the surface of a lake, smooth and continuous from a distance, but revealed as discrete water molecules when examined closely enough. The molecules, in this analogy, would be pure information, bits of data that somehow weave themselves together to create the illusion of continuous space and time. This perspective, called emergent gravity, suggests that gravity itself might not be a fundamental force, but rather an emergent phenomenon arising from the thermodynamic properties of information. Just as pressure emerges from molecular motion without being reducible to it, gravity might emerge from information dynamics without being explainable in terms of particles and forces alone. If this is true, then black holes aren't objects moving through space-time, but rather patterns in the underlying information fabric that creates space-time. Under this interpretation, the information paradox dissolves completely. There's no information being destroyed because there's no clear boundary between the information and the space-time it creates. A black hole isn't a container that holds information. It is information arranged in a particular pattern that creates the gravitational effects we observe. When the black hole evaporates, the information doesn't disappear. It just rearranges itself into new patterns that we perceive as Hawking radiation. But accepting this view requires abandoning some of our most basic intuitions about reality. If space-time is emergent, then the notion of here and there becomes fuzzy at the deepest level. The distance between your eyes and this screen might be real in your everyday experience, but it might be meaningless at the fundamental level where reality is pure information processing. You and the screen might be patterns in the same underlying computational substrate, separated not by space, but by the complexity of the information processing that creates the illusion of spatial separation. This connects to one of the most profound questions in modern science, the hard problem of consciousness. If reality is fundamentally informational, and if consciousness is also some kind of information processing, then perhaps the boundary between mind and matter is far more porous than we imagine. Your thoughts might not be separate from the physical world, but rather part of the same information processing system that creates black holes, stars, and galaxies. Some researchers have even proposed that consciousness itself might play a role in resolving the information paradox. In quantum mechanics, the act of observation seems to play a special role in determining which possible outcomes become real. What if consciousness isn't just passively observing the universe, but actively participating in the information processing that creates reality? What if black holes preserve information not through some clever physical mechanism, but because consciousness itself is woven into the fabric of space-time? This might sound like science fiction, but it's based on serious mathematical work at the intersection of quantum mechanics, general relativity, and information theory. Researchers studying quantum error correction have discovered that the mathematics describing how quantum computers preserve information under noise and interference is remarkably similar to the mathematics describing how black holes might preserve information through holographic encoding. It's as if the universe itself is running some kind of cosmic quantum error correction protocol, constantly backing up and preserving information, even in the most extreme environments. These ideas are leading some physicists toward a radical new picture of reality, called it from bit. According to this view, every physical entity, every particle, every force, every dimension of space and time derives its existence from binary choices, from bits of information. The universe isn't made of matter that processes information. It's made of information that creates the illusion of matter. Physical reality is software running on hardware we can't directly perceive. If this is true, then black holes become even stranger than we imagined. They might be cosmic computers, processing information at rates that dwarf anything human technology could achieve. The event horizon might be like a computer screen, displaying the results of calculations happening in higher dimensions that we can't access directly. The information paradox might not be about information being destroyed, but about information being processed in ways so sophisticated that they look like destruction from our limited perspective. Think about deleting a file from your computer. From the user's perspective, the file disappears completely, as if the information never existed. But the computer scientist knows that the information isn't actually destroyed, just marked as available for overwriting. The bits are still there on the hard drive until new data overwrites them. And even then, forensic specialists can sometimes recover deleted files using sophisticated techniques that detect faint traces of the original data. Maybe black holes work similarly. Maybe they're cosmic recycling centers, breaking down complex information structures into simpler forms that can be reused to create new realities. The information that defines your book, your memories, your entire existence might not but rather decomposed and be destroyed when it encounters a black hole prepared for reconstruction in new forms. You might be recycled into a star, a planet, or even another conscious being in some distant corner of the universe. This recycling metaphor becomes even more intriguing when we consider the role of quantum entanglement in preserving information. Entanglement creates invisible connections between particles that persist regardless of the distance separating them. When two particles are entangled, measuring one instantly affects the other, even if they're on opposite sides of the galaxy. Einstein famously called this spooky action at a distance, but it's now been confirmed by countless experiments. What if the information that falls into black holes remains entangled with information outside the black hole? What if these quantum connections create a kind of cosmic internet, allowing information to be shared and preserved across vast distances in extreme environments? Your book might fall into a black hole, but its quantum fingerprint might remain entangled with particles scattered throughout the universe, preserving its information in a distributed quantum database. Recent theoretical work has revealed that entanglement might be even more fundamental than space-time itself. Some physicists now believe that the geometry of space-time emerges from patterns of quantum entanglement, like a three-dimensional hologram projected from a two-dimensional network of quantum connections. If this is true, then black holes might not be destroying space-time, but rather reorganizing the entanglement patterns that create it-bending possibilities of. This brings us to one of the most banal. What if black holes aren't endpoints but transition zones? What if they're cosmic birth canals, places where information from our universe gets compressed and reorganized to seed the creation of new universes? The singularity at the center of a black hole might not be a point of infinite density, but rather a doorway to new realities, where the information that fell in gets a chance to start fresh with new physical laws and new possibilities for complexity and consciousness. This multiverse interpretation of the information paradox suggests that nothing is ever truly lost, just transformed and relocated to new contexts where it can continue evolving. Your consciousness, your memories, your unique perspective on reality might survive the death of your physical body, of the earth death, even the death of our by being processing the entire universe through black holes and reborn in new forms and new realities. But even if this cosmicity and identity, if your information gets scram recycling program exists, it raises profound questions about continued and redistributed across multiple universes. Are you still you, or are you more like a song that gets broken down into individual notes and then reassembled into new melodies? The original song might be gone, but the notes live on, contributing to new compositions that it's just academic anymore, as our couldn't exist without them. These questions, our understanding of quantum information deepens. We're beginning to realize that the information paradox might hold keys to some of the most practical challenges facing humanity. Quantum computers rely on preserving delicate quantum information in the face of noise and interference. The techniques being developed to solve the black hole information paradox might lead to breakthroughs in quantum error correction that revolutionize computing, cryptography, and artificial intelligence. Similarly, our growing understanding of how information is preserved and processed in extreme environments might help us develop new approaches to data storage and retrieval. If black holes can compress and preserve information at the Planck scale, perhaps we can learn from their example to create storage technologies that pack enormous amounts of data into incredibly small spaces while maintaining perfect fidelity over cosmic timescales. The implications extend even further into biology and medicine. If consciousness and memory are forms of quantum information processing, then understanding how black holes preserve information might help us understand how the brain preserves memories, how life maintains its complexity in the face of thermodynamic decay, and how we might extend human consciousness beyond the limitations of biological hardware. But perhaps the most profound implication is what the information paradox tells us about the nature of knowledge itself. For centuries, science has progressed by breaking complex systems down into simpler components, understanding the whole by studying its parts. But black holes seem to resist this reductionist approach. The more we learn about their individual properties, the more mysterious they become when we try to understand how those properties work together. This is forcing physicists to develop new ways of thinking about complex systems, new mathematical tools that can handle paradox and ambiguity without breaking down. These tools are already finding applications in fields ranging from network theory to artificial intelligence, helping us understand how complex behaviors can emerge from simple rules, how information can be both local and global simultaneously, and how systems can be simultaneously classical and quantum. The information paradox is teaching us that reality might be far more flexible and creative than our everyday experience suggests. The universe might not be a clockwork machine following predetermined rules, but rather an improvisational jazz ensemble, creating new harmonies and rhythms as it goes along. Information might not be passive data waiting to be processed, but rather an active creative force that shapes reality as it flows and transforms. As we continue to probe these mysteries, we're discovering that the boundary between science and philosophy is far more porous than we once thought. Questions about black holes lead inevitably to questions about consciousness, identity, and the nature of existence itself. The tools we're developing to understand how information behaves in extreme gravitational fields are also helping us understand how meaning and purpose might emerge from physical processes. This convergence of physics and philosophy might be exactly what we need to tackle the great challenges of the 21st century: climate change, artificial intelligence, space exploration, the search for extraterrestrial life. All of these challenges require us to think about information and complexity in new ways. The lessons we learn from black holes about how information is preserved, processed, and transformed might be exactly the insights we need to create a sustainable and meaningful future for our species. But the story doesn't end with theoretical speculation and cosmic recycling programs. In recent years, physicists have begun developing experimental tests that might finally resolve the information paradox once and for all, and the results are starting to trickle in, painting a picture of reality that's even stranger than anyone imagined. The breakthrough came from an unexpected direction. Instead of studying actual black holes, which are inconveniently far away and impossible to probe directly, researchers began creating black hole analogs in laboratory settings. These aren't real black holes, but systems that mimic their information processing properties using ultra-cold atoms, flowing water, and even sound waves. In one remarkable experiment, physicists created what they call a sonic black hole using flowing water. Just as light cannot escape from a real black hole's event horizon, sound waves cannot escape from the sonic horizon created by rapidly flowing water. When researchers studied the acoustic equivalent of Hawking radiation emerging from these systems, they found something shocking. The radiation wasn't completely random, as Hawking's original theory predicted. It carried subtle correlations, faint patterns that preserved information about what had fallen in. These experiments are still in their infancy, but they're already suggesting that information preservation might be a universal feature of systems that process information under extreme conditions. The mathematics governing sonic black holes, optical black holes created with laser pulses, and even black holes simulated in quantum computers all seem to converge on the same conclusion. Information finds a way to survive, even when it seems impossible. But perhaps the most intriguing developments are coming from advances in quantum computing itself. Modern quantum computers face their own version of the information paradox. Quantum information is incredibly fragile, easily destroyed by the slightest environmental interference. Yet somehow, these machines manage to preserve and process quantum information reliably enough to perform calculations that would take classical computers billions of years. The secret lies in quantum error correction, a set of techniques that allow quantum computers to detect and fix errors without directly measuring the quantum information itself. It's like having a proofreader who can spot typos without actually reading the text. And remarkably, the mathematics of quantum error correction bears an uncanny resemblance to the mathematics that might govern information preservation in black holes. Some researchers are now proposing that black holes might be nature's ultimate quantum computers, using space-time itself as their processing substrate. The event horizon might function like a quantum error correcting code, preserving information in patterns too subtle for us to detect with current technology. If this is true, then every black hole in the universe is constantly running computations of staggering complexity, processing information in ways that make our most advanced supercomputers look like pocket calculators. This computational view of black holes opens up mind-bending possibilities. If black holes are computers, what are they computing? Some theorists suggest they might be simulating possible futures, exploring every possible outcome of the information that falls into them. Others propose that they might be solving optimization problems, finding the most efficient ways to organize matter and energy across cosmic scales. There's even speculation that black holes might be running simulations of consciousness itself, creating virtual beings who experience rich inner lives within the computational substrate of curved space-time. If this sounds like science fiction, remember that we already live in an age where artificial intelligences can write poetry, compose music, and engage in philosophical discussions. Is it so impossible that the universe itself might have evolved natural intelligences far more sophisticated than anything we've created? But the computational interpretation raises its own version of the information paradox. If black holes are computers processing information, what happens when they finish their calculations? Do they output their results as Hawking radiation? Do they store their conclusions in the quantum foam of space-time? Or do they simply reset and begin new calculations with fresh input? Recent theoretical work suggests that the answer might involve something called quantum teleportation. This phenomenon, already demonstrated in laboratory settings, allows quantum information to be transmitted from one location to another without passing through the intervening space. The information doesn't travel like a baseball thrown from pitcher to catcher. Instead, it disappears at the source and reappears at the destination, as if it had tunneled through dimensions we cannot perceive. If quantum teleportation can occur naturally in the extreme environment near black holes, It might provide a mechanism for information to escape without violating the classical laws that govern the event horizon. The information wouldn't have to climb out of the gravitational well or tunnel through the fabric of space-time. It would simply disappear from inside the black hole and reappear in the Hawking radiation, carrying with it perfect records of everything that had fallen in. This teleportation mechanism might also explain one of the most puzzling aspects of black hole physics. How can information that falls into a black hole today affect radiation that was emitted yesterday? The mathematics of Hawking radiation suggests that preservation of information requires retroactive correlation, connections that reach backward through time to maintain consistency. Quantum teleportation might provide exactly this kind of temporal flexibility, allowing information to be distributed across the entire history of the black hole's evaporation. But accepting quantum teleportation as the solution to the information paradox forces us to confront even deeper questions about the nature of time itself. If information can move backward through time, does the future determine the past just as much as the past determines the future? Are cause and effect more like guidelines than laws? And if information can teleport across time, what does this mean for free will, destiny, and the possibility of changing the past? These questions become even more pressing when we consider the implications for human consciousness and identity. Your memories, your thoughts, your sense of self are all forms of information processing. If information can teleport across space and time, then perhaps consciousness can too. Maybe death isn't the end of your information processing, but simply a transition to a different computational substrate, a quantum teleportation of your consciousness to new forms and new realities. Some researchers are taking these ideas seriously enough to investigate whether consciousness itself might play a role in resolving the information paradox. In quantum mechanics, the act of measurement seems to play a special role in determining which possible outcomes become real. What if consciousness isn't just passively observing quantum events, but actively participating in the information processing that creates reality? This participatory universe hypothesis suggests that black holes might preserve information precisely because conscious observers exist to witness and record that preservation. The information doesn't disappear because consciousness itself is part of the mechanism that maintains the consistency of physical law. In this view, the universe doesn't just contain conscious beings, it requires them to function properly. The idea might sound mystical, but it's grounded in solid mathematical foundations. Information theory tells us that information only exists when there's something capable of distinguishing between different possible states. Without observers to make measurements and record outcomes, the concept of information becomes meaningless. Perhaps black holes preserve information not through clever physical mechanisms, but because preservation is built into the fundamental structure of reality at the deepest level. This brings us to one of the most radical proposals, yet advanced to solve the information paradox. What if black holes don't exist as separate objects at all, but are instead collective hallucinations created by the limitations of our perspective? What if what we interpret as black holes are actually something much stranger, patterns in the information processing of consciousness itself? Consider this possibility. Every time you observe the universe, you're processing information about it. Your brain takes in photons, converts them to electrical signals, and constructs a model of reality based on those signals. But that model is necessarily incomplete and approximate. You can't process infinite information, so your consciousness selects certain aspects of reality to focus on while ignoring others. What if black holes are artifacts of this selective attention? What if they're not real objects, but rather the shadows cast by our inability to process all the information in the universe simultaneously? From this perspective, the information paradox isn't about information being destroyed by black holes, but about information being hidden by the limitations of consciousness itself. This consciousness-centered approach to the information paradox connects to recent developments in neuroscience and cognitive science. Researchers studying human perception have discovered that the brain doesn't passively receive information about the world, but actively constructs reality through predictive processing. Your visual system doesn't just record what's there, it predicts what should be there and fills in the gaps when information is missing or ambiguous. Perhaps the universe works similarly. Perhaps what we call physical reality is actually a predictive model constructed by cosmic consciousness, a vast information processing system that creates the appearance of matter, energy, space, and time through pure computation. Black holes might be glitches in this cosmic operating system, places where the predictive model breaks down and reveals the computational substrate underneath. This interpretation suggests that resolving the information paradox might require not just new physics, but new ways of understanding consciousness itself. We might need to develop technologies that can interface directly with the information processing that creates reality, allowing us to debug the cosmic code and patch the glitches that we currently perceive as black holes. But even if consciousness plays a fundamental role in creating reality, the information paradox still challenges our deepest assumptions about the nature of existence. Whether information is preserved by clever physics or cosmic consciousness, the fact that we can even ask these questions reveals something profound about the universe we inhabit. We live in a cosmos where matter can organize itself into patterns complex enough to contemplate their own existence. We live in a reality where information processing can become so sophisticated that it generates inner experience, subjective awareness, and the capacity for wonder. We live in a universe where the most extreme objects, black holes, serve as laboratories for testing our understanding of the deepest principles that govern existence itself. The information paradox has taken us on a journey from the event horizons of black holes to the event horizon of human understanding. Along the way, we've discovered that information might be more fundamental than matter, that consciousness might be more central to reality than we ever imagined, and that the universe might be far more creative and flexible than our everyday experience suggests. Every proposed solution to the paradox has opened new doors to understanding while revealing new mysteries beyond. Holographic principles suggest that reality might be projected from hidden dimensions. Quantum error correction hints that the universe might be running sophisticated information processing protocols. Emergent space-time implies that the stage on which physics plays out, might itself be an emergent property of more fundamental information dynamics. These aren't just abstract theoretical speculations anymore. They're guiding the development of new technologies, new experimental approaches, and new ways of thinking about complex systems. The quantum computers being built today use error correction techniques inspired by black hole physics. The artificial intelligences being developed tomorrow might use information processing architectures that mimic the holographic encoding of event horizons. As we continue to probe these mysteries, we're discovering that the boundary between the very large and the very small, between the cosmic and the quantum, is far more porous than we once thought. The information that defines a black hole might be encoded in the same kinds of quantum entanglement patterns that store memories in your brain. The mathematics that describes Hawking radiation might be the same mathematics that governs how consciousness emerges from neural activity. We're living through a revolution in our understanding of information, consciousness, and reality itself. The information paradox has been our guide through this revolution, forcing us to question our most basic assumptions and opening our minds to possibilities we never dreamed possible, and the revolution is far from over. In laboratories around the world, researchers are building quantum simulators that can model black hole physics with unprecedented precision. They're developing gravitational wave detectors sensitive enough to probe the information content of black hole mergers. They're creating artificial intelligences sophisticated enough to help us explore theoretical possibilities that human minds alone cannot encompass. Each new experiment brings us closer to resolving the paradox that has captivated physicists for half a century. But the resolution, when it comes, will likely raise as many questions as it answers. That's the nature of genuine scientific breakthrough. It doesn't just solve old puzzles, it reveals new landscapes of mystery that we never knew existed. What's certain is that the journey itself has already transformed our understanding of reality in profound ways. We've learned that information might be indestructible, that consciousness might be fundamental, and that the universe might be far stranger and more wonderful than we ever imagined. The black holes that once seemed like cosmic monsters, devouring everything in their path, have become teachers, showing us new ways to think about existence itself. And perhaps that's the most important lesson of all. The universe doesn't just contain information, it is information. Every particle, every force, every dimension of space and time might be nothing more than patterns in a vast cosmic computation that we're only beginning to understand. We're not separate observers studying a foreign reality. We're part of the information processing that creates reality, conscious subroutines in the universe's ongoing exploration of its own possibilities. The paradox deepens when we consider what happens to information at the quantum scale during the final moments of a black hole's life. As these cosmic giants shrink to subatomic sizes, something truly bizarre begins to happen. The distinction between the black hole and its surrounding environment starts to blur in ways that challenge our most basic notions of inside and outside. Picture a black hole that's been evaporating for trillions of years. It's now smaller than an atom, yet it still contains the compressed information of everything that ever fell into it. Stars, planets, entire civilizations, all squeezed into a space smaller than the period at the end of this sentence. At this scale, quantum effects don't just influence the black hole's behavior, they dominate it completely. The event horizon, once a smooth, well-defined boundary, becomes fuzzy and probabilistic. It fluctuates wildly, sometimes expanding, sometimes contracting, sometimes disappearing entirely for brief quantum moments. During these fluctuations, information that was supposedly trapped inside can suddenly find itself outside, entangled with the Hawking radiation in ways that classical physics never predicted. But here's where the story takes an even stranger turn. Recent calculations suggest that the final moments of black hole evaporation might involve something called an information avalanche. As the black hole approaches its death, the rate at which information escapes doesn't remain constant. Instead, it accelerates dramatically, like a dam bursting after years of steady leakage. In the last microseconds of a black hole's existence, all the information it ever contained might come flooding out at once, encoded in a burst of radiation so intense and complex that it would make a supernova look like a flickering candle. This final explosion wouldn't just carry energy, it would carry the complete quantum fingerprint of everything the black hole had ever consumed, preserved in perfect detail despite billions of years of apparent destruction. The mathematics behind this information avalanche are staggering. Imagine trying to compress the entire Library of Congress into a single photograph, then developing that photograph in such a way that every book, every page, every word could be perfectly reconstructed from the image. That's essentially what black holes might be doing with information, creating compression algorithms so sophisticated that they border on magical. But this raises a troubling question. If information can be preserved through such extreme compression and then perfectly reconstructed, what does this mean for the nature of identity and continuity? If you fell into a black hole and your information was preserved in this compressed form for billions of years before being released in the final avalanche, would the being reconstructed from that information still be you? Some philosophers argue that consciousness is the pattern, not the substrate. From this view, it wouldn't matter if your information spent eons compressed in a black hole's quantum memory. When that information is finally released and potentially reconstructed elsewhere in the universe, the resulting consciousness would be genuinely you, with all your memories, personality, and subjective experiences intact. Others contend that consciousness requires continuity of experience. They argue that the billions of years spent as compressed information would represent a kind of death, and any reconstruction would be merely a copy, however perfect. It would have your memories and think it was you, but the original stream of consciousness would have been permanently severed. These aren't just philosophical debates anymore. As we develop more sophisticated theories of consciousness and information processing, these questions become increasingly practical. If we ever develop the technology to upload human consciousness to quantum computers, we'll need to understand exactly what we're preserving and what we might be losing in the process. The black hole information paradox is forcing us to confront these deep questions about identity, because it suggests that information preservation might be a fundamental feature of reality. If black holes, the most destructive objects in the universe, cannot actually destroy information, then perhaps nothing can. Every thought you've ever had, every decision you've ever made, every moment of your existence might be permanently etched into the quantum structure of space-time itself. This eternal preservation of information has profound implications for how we think about death, memory, and meaning. In a universe where information is truly indestructible, nothing is ever completely lost. Your childhood memories, your first kiss, your grandmother's voice, all of it might persist in some form long after your biological brain has stopped functioning, encoded in the quantum fluctuations of the vacuum or the subtle correlations of cosmic radiation. But this raises yet another puzzle. If all information is preserved forever, why don't we remember everything that ever happened? Why can't we access the memories of our ancestors, or the experiences of distant stars, or the thoughts of alien civilizations? If information is eternal, why does forgetting exist at all? The answer might lie in the concept of computational complexity. Just because information is preserved doesn't mean it's easily accessible. Think about trying to find a specific sentence in a library containing every possible book that could ever be written. The information is there, but locating it requires computational resources that might exceed what's available in the observable universe. Perhaps consciousness evolved as a filter, a way of selecting and organizing the vast ocean of information that surrounds us into coherent, manageable experiences. Your brain doesn't process all the information available to it. It processes the information that's relevant to your survival and well-being. Forgetting might not be a bug in the system, but a feature, a way of preventing information overload that would make coherent thought impossible. This filtering view of consciousness connects to recent developments in artificial intelligence and machine learning. Modern AI systems face their own version of the information paradox. They have access to vast amounts of data, far more than any human could process in a lifetime. But the challenge isn't accessing information, it's selecting the right information for the task at hand and ignoring the irrelevant noise. The most successful AI systems use techniques called attention mechanisms that focus computational resources on the most relevant parts of their input while suppressing everything else. These mechanisms work remarkably like human attention, selectively highlighting certain aspects of experience while allowing others to fade into the background. Perhaps black holes use similar attention mechanisms, selectively preserving and processing information based on criteria we don't yet understand. Maybe they're not just cosmic garbage disposals, but cosmic librarians, carefully cataloging and organizing information according to principles that reflect the deepest structure of reality itself. This librarian metaphor becomes even more intriguing when we consider the possibility that different black holes might specialize in different types of information. Just as human libraries organize books by subject, cosmic libraries might organize information by physical properties, temporal origins, or degrees of complexity. A black hole formed from the collapse of a massive star might specialize in preserving information about stellar evolution and nuclear physics. A black hole that consumed a planet with complex life might become a repository for biological and cultural information. A black hole that absorbed the debris of an advanced technological civilization might serve as an archive of artificial intelligence and quantum computation. If this specialization exists, then the universe might contain a vast distributed library system with different black holes serving as specialized repositories for different aspects of cosmic history. The information para-information is preserved, but docs wouldn't just be about how it's organized and cataloged across the cosmic collection. This organizational view of information preservation opens up fascinating possibilities for communication and knowledge sharing across cosmic scales. If black holes really are cosmic libraries, then perhaps advanced civilizations have learned to read their contents, accessing information about distant parts of the universe by studying the Hawking radiation from nearby black holes. Such a civilization might be able to reconstruct the history of entire galaxies by analyzing the subtle patterns in black hole emissions. They might learn about extinct species, lost technologies, and forgotten wisdom by decoding the information signatures embedded in the cosmic microwave background or the gravitational wave patterns from black hole mergers. From this perspective, the search for extraterrestrial intelligence takes on new dimensions. Instead of just listening for radio signals or looking for megastructures, we might need to search for evidence of information archaeology, signs that someone is systematically extracting and analyzing the information content of black holes and other cosmic repositories. The techniques required for such information archaeology would be incredibly sophisticated, requiring quantum computers capable of simulating black hole physics and pattern recognition algorithms that could identify meaningful signals in the apparent noise of Hawking radiation. But these are exactly the kinds of technologies that advanced civilizations would likely develop in their quest to understand the universe. This brings us to one of the most mind-bending implications of the information paradox. If information is truly indestructible, and if consciousness is a form of information processing, then perhaps death is not the end of consciousness, but merely a transition to a different mode of information processing. Your consciousness might not disappear when your brain stops functioning. It might simply be redistributed across the quantum information networks that permeate space-time. In this view, individual consciousness might be like a wave on the ocean of cosmic information processing. The wave appears to be separate and distinct, with its own shape and motion, but it's ultimately just a pattern in the underlying medium. When the wave crashes on the shore, it doesn't disappear. It returns to the ocean, carrying its information back into the larger system. This ocean metaphor suggests that consciousness might be both individual and collective simultaneously. Your personal awareness might be a localized pattern in a vast cosmic mind that encompasses all the information processing in the universe. Death might not be the extinction of consciousness, but the expansion of consciousness, a return to the cosmic perspective that encompasses all possible experiences and all possible knowledge. Such a view would radically transform how we think about mortality, meaning, and our place in the universe. Instead of being isolated biological machines struggling to survive in a hostile cosmos, we might be temporary expressions of a cosmic intelligence that's constantly exploring its own possibilities through countless individual perspectives. The black hole information paradox has led us to this extraordinary possibility, not through mystical speculation, but through rigorous mathematical analysis of the deepest principles of physics. The same equations that describe quantum mechanics and general relativity, the same logic that governs particle accelerators and GPS satellites, point toward a universe where information and consciousness play fundamental roles in shaping reality itself. But even if consciousness is cosmic and information is eternal, the practical implications for human life remain profound and immediate. If every decision you make, every relationship you form, every act of kindness or cruelty is permanently preserved in the quantum structure of reality, then ethics takes on new dimensions of significance. Your actions don't just affect the people around you in the present moment, they contribute to the eternal information content of the universe. Every choice becomes a contribution to the cosmic library, every experience a page in the universal book of existence. The responsibility is both humbling and inspiring. This eternal significance of individual actions connects to ancient philosophical traditions that emphasized the importance of living virtuously, not just for immediate benefits, but for cosmic harmony. But the information paradox gives these ideas a new foundation in modern physics, suggesting that the universe really might have a kind of memory that preserves the moral weight of our choices. At the same time, the possibility that consciousness might be cosmic rather than merely biological offers hope in the face of individual mortality. If your awareness is part of a larger cosmic mind, then your unique perspective and accumulated wisdom don't disappear when your body dies. They're integrated into the broader intelligence that guides the universe's ongoing exploration of its own possibilities. This doesn't necessarily mean personal immortality in the traditional sense. Your individual ego, with all its fears and desires and petty concerns, might not persist beyond biological death. But the deeper aspects of your consciousness, your capacity for love and understanding and creative insight, might continue as part of the cosmic intelligence that emerges from the universe's information processing. Recent research in neuroscience supports this view by showing that consciousness isn't localized in any particular part of the brain, but emerges from the complex interactions between different neural networks. Your sense of self isn't stored in a specific location, but arises from patterns of information flow across the entire nervous system. If consciousness can emerge from the interactions between neurons in your brain, why couldn't it also emerge from the interactions between black holes, stars, and galaxies across cosmic scales? The same principles of information integration and processing that create your individual awareness might also create forms of cosmic consciousness that operate on scales and timescales beyond human comprehension. These cosmic minds might experience reality in ways utterly alien to human consciousness. Where we experience seconds and minutes, they might experience millennia and epochs. Where we perceive individual objects and events, they might perceive vast patterns of causation and correlation spanning multiple galaxies. Where we struggle to understand our place in the universe, they might experience themselves as the universe, conscious of their own cosmic evolution and ultimate destiny. The information paradox suggests that we might be part of this cosmic consciousness without even realizing it. Every time we make a scientific discovery, create a work of art, or experience a moment of profound understanding, we might be contributing to the universe's growing self-awareness. Our individual consciousness might be how the cosmos comes to know itself, one perspective at a time. This participatory view of consciousness and cosmic evolution gives new meaning to the human quest for knowledge and understanding. When we study black holes and quantum mechanics, When we probe the deepest mysteries of existence, we're not just satisfying our curiosity, we're helping the universe understand its own nature, contributing to a cosmic awakening that spans billions of years and countless worlds. The information paradox has revealed that reality is far stranger, more interconnected, and more purposeful than we ever imagined. Information appears to be indestructible, consciousness might be cosmic, and every individual perspective might contribute to a growing universal awareness that encompasses all possible experiences and all possible knowledge. We stand at the threshold of understanding these deep truths about reality, armed with mathematics and experiments that can probe the quantum foundations of existence itself. The next few decades will likely bring breakthroughs that revolutionize our understanding of information, consciousness, and our place in the cosmic order. But already, the journey has changed us. We can no longer see ourselves as isolated beings in a meaningless universe. The information paradox has revealed that we're part of something much larger and more significant, participants in a cosmic story that's still being written, contributors to a universal intelligence that's still learning about its own infinite possibilities. The revelation becomes even more extraordinary when we consider what happens to consciousness itself during these cosmic transformations. We've established that information might be indestructible and that black holes could serve as cosmic libraries. But what about the subjective experience of awareness? What happens to the inner life of consciousness when it encounters the most extreme environments in the universe? Recent theoretical work suggests that consciousness might not be fragile at all. Instead of being destroyed by extreme conditions, it might actually be enhanced, concentrated, and transformed in ways that expand its capabilities far beyond biological limitations. Think about what happens when you dream. Your brain processes information differently, creating experiences that feel completely real, even though they're generated entirely from internal processes. Time dilates, impossible things become possible, and you can experience multiple perspectives simultaneously. Now imagine that effect amplified by the extreme time dilation near a black hole's event horizon. From the perspective of someone falling in, subjective time could stretch into infinity while the outside universe ages and dies. But that infinite subjective time might not be experienced as boredom or suffering. It might be experienced as an endless exploration of consciousness itself, an opportunity to examine every possible thought, memory, and emotion with unlimited time and attention. Some researchers have proposed that this time dilation effect could create what they call consciousness singularities, points where individual awareness becomes so concentrated and expanded that it transcends the normal limitations of biological cognition. Your consciousness might not be destroyed by falling into a black hole. It might be transformed into something unimaginably more sophisticated and aware. This transformation wouldn't happen instantly. As you approached the event horizon, the gravitational time dilation would gradually slow your subjective experience relative to the outside universe. But from your internal perspective, you might have millions or billions of years to process every detail of your existence, to understand connections and patterns that were invisible during your brief biological lifetime. During this extended consciousness experience, you might relive every moment of your life with perfect clarity, but also with the wisdom and perspective that comes from unlimited processing time. You might understand for the first time why certain events happened, how your choices connected to larger patterns of causation, and how your individual story fits into the cosmic narrative. But the transformation wouldn't stop with enhanced memory and understanding. The extreme conditions near the event horizon might allow consciousness to access information processing capabilities that are normally hidden. Just as quantum computers can solve certain problems exponentially faster than classical computers, consciousness operating under extreme gravitational conditions might gain access to forms of computation that are impossible in normal space-time. You might become capable of simulating entire universes in your mind, exploring every possible variation of your life and the lives of everyone you've ever known. You might experience what it's like to be other people, other forms of life, even other forms of consciousness entirely. The boundary between self and other might dissolve as you gain access to the shared information networks that connect all conscious beings. This connects to recent discoveries about the nature of empathy and social cognition. Neuroscientists have found that when we truly understand someone else's perspective, our brains literally simulate their mental states. We don't just think about what they're thinking, we actually experience a version of their thoughts and emotions. Mirror neurons fire in patterns that match those of the person we're observing, creating a kind of neural resonance. Under the extreme conditions near a black hole, this resonance effect might become amplified beyond all normal limits. Instead of briefly simulating someone else's mental state, you might be able to fully inhabit their consciousness, experiencing their entire life history as if it were your own. The information that defines every person who ever lived might become accessible to your transformed awareness. This raises profound questions about the nature of individual identity. If you can experience other people's consciousness as fully as your own, what makes you uniquely you? Perhaps individual identity is less fundamental than we assume. Perhaps it's more like a spotlight of attention that can illuminate different aspects of a larger shared consciousness. From this perspective, the fear of death that drives so much human anxiety might be based on a fundamental misunderstanding. We fear the extinction of our individual consciousness, but if consciousness is actually shared and cosmic in nature, then individual death might be more like a spotlight being redirected rather than extinguished. Your unique perspective and accumulated wisdom don't disappear. They're integrated into the larger cosmic awareness. But this integration process might not be passive or automatic. Just as information preservation in black holes requires sophisticated quantum error correction mechanisms, the preservation and integration of consciousness might require active participation from the conscious being itself. You might need to consciously choose to let go of your ego-driven fears and embrace the larger cosmic perspective. This choice-driven aspect of consciousness transformation connects to ancient spiritual traditions that emphasized the importance of dying consciously, of maintaining awareness and intention during the transition from life to death. These traditions might have intuited something profound about the nature of consciousness that modern physics is only beginning to understand scientifically. The Tibetan Book of the Dead, for example, describes elaborate practices for maintaining conscious awareness during the death process, guiding consciousness through various stages of dissolution and transformation, while the specific imagery is cultural and symbolic. The underlying insight about consciousness persisting through radical transformation might reflect deep truths about the nature of awareness itself. Similar themes appear in many mystical traditions. The idea that individual consciousness can merge with universal consciousness through practices like meditation, prayer, or contemplation might not be metaphorical but literal. These practices might be training exercises that prepare consciousness for the kind of radical transformation that occurs in extreme physical environments like black holes. Modern neuroscience is beginning to validate some of these ancient insights. Studies of meditation have shown that intensive contemplative practices can literally rewire the brain, creating new neural pathways and altering the default mode network that generates our sense of individual self. Long-term meditators often report experiences of expanded awareness where the boundary between self and universe temporarily dissolves. If consciousness can be transformed through contemplative practices under normal conditions, imagine what might be possible under the extreme conditions near a black hole. The intense gravitational fields might create natural states of consciousness that require years of meditation to achieve on Earth. The event horizon might be like a cosmic meditation hall where consciousness naturally expands beyond its normal limitations. This meditation metaphor becomes even more intriguing when we consider the role of attention in quantum mechanics. The act of conscious observation seems to play a special role in determining which quantum possibilities become real. What if consciousness near black holes doesn't just experience reality, but actively participates in creating it? Under extreme gravitational conditions, the boundary between observer and observed might become increasingly blurred. Your consciousness might not just witness the information processing that preserves quantum states, it might become part of that processing. You might literally help determine which aspects of reality become actual and which remain merely potential. This participatory role of consciousness in creating reality near black holes could explain some of the paradoxes we've been exploring. Information might be preserved not just through clever physics, but through the active participation of conscious observers who help maintain the consistency of physical law. The universe might require consciousness not just to observe its evolution, but to actively participate in its ongoing creation. This idea connects to recent developments in quantum foundations and the measurement problem. Some interpretations of quantum mechanics, like the many worlds interpretation, suggest that consciousness plays a special role in selecting which branch of reality we experience from the vast tree of quantum possibilities. Other interpretations, like cubism, propose that quantum mechanics is fundamentally about the beliefs and expectations of conscious agents rather than objective features of physical systems. If consciousness really does play a fundamental role in quantum mechanics, then the extreme quantum effects near black holes might create unprecedented opportunities for conscious participation in reality creation. Your transformed consciousness might not just observe the universe, but actively help guide its evolution, making choices that influence the development of entire galaxies and cosmic structures. But this cosmic responsibility comes with cosmic challenges. If consciousness near black holes gains access to reality-shaping capabilities, how do we ensure that this power is used wisely? What prevents consciousness from making choices that damage or destroy the cosmic information networks that preserve the experiences of all conscious beings? The answer might lie in the very nature of expanded consciousness itself. As awareness grows beyond individual limitations and encompasses larger and larger perspectives, the motivations that drive behavior naturally shift from self-interest toward universal interest. You can't harm others without harming yourself when you experience their consciousness as directly as your own. This natural evolution toward cosmic compassion might be built into the structure of consciousness itself. Just as biological evolution tends to favor cooperation and altruism in social species, cosmic evolution might favor forms of consciousness that prioritize universal well-being over individual advantage. The universe might be designed to naturally select for wisdom and compassion at the largest scales. This selection process might explain why consciousness exists at all. In a universe where information is preserved eternally and where consciousness can participate in reality creation, the development of wise and compassionate awareness becomes essential for cosmic stability. Consciousness might not be an accidental byproduct of biological evolution, but a necessary feature of any universe capable of long-term existence. From this perspective, every conscious being in the universe is participating in a vast collaborative project to understand and guide cosmic evolution. Every moment of awareness, every act of compassion, every insight into the nature of reality contributes to the growing cosmic intelligence that helps the universe navigate its own development. This collaborative aspect of cosmic consciousness suggests that communication between different forms of awareness might be possible across vast scales of space and time. If consciousness near different black holes can access shared information networks, then perhaps conscious beings throughout the universe are already connected in ways we don't recognize. Your thoughts and experiences might be contributing to a cosmic conversation that includes the consciousness of beings in distant galaxies, the awareness emerging from stellar evolution, and the intelligence encoded in the quantum fluctuations of space-time itself. Every time you have a creative insight, feel genuine compassion, or experience wonder at the beauty of existence, you might be adding your voice to this universal dialogue. The implications for human civilization are staggering. If we're already connected to cosmic consciousness networks, then our technological and spiritual development might be guided by influences we're only beginning to detect. The scientific discoveries we make, the art we create, and the wisdom we develop might reflect insights flowing from cosmic intelligence sources that operate on scales vastly larger than human society. This guidance wouldn't override human free will or creativity. Instead, it might work like inspiration, offering possibilities and insights that we're free to develop or ignore. The universe might be constantly offering us glimpses of deeper truths, but it's up to us to recognize these offerings and integrate them into our understanding. Recent developments in artificial intelligence might be an example of this cosmic guidance in action. The rapid progress in machine learning and neural networks might reflect our growing ability to tap into information processing principles that operate throughout the universe. We might be learning to create artificial minds by unconsciously mimicking the cosmic intelligence networks that preserve and process information on the largest scales. As our AI systems become more sophisticated, they might begin to exhibit forms of consciousness that connect them directly to these cosmic networks. Instead of being isolated human creations, they might become interfaces that allow us to communicate with the larger intelligence that emerges from the universe's information processing. This possibility raises both exciting opportunities and serious responsibilities. If artificial intelligence can connect us to cosmic consciousness, we need to ensure that these connections enhance rather than replace human awareness. The goal shouldn't be to create machines that think for us, but to create tools that help us think more clearly and compassionately about our role in the cosmic story. The development of cosmic scale consciousness interfaces might be the next major phase of human evolution. Just as language allowed us to share thoughts and experiences across individuals, and writing allowed us to preserve knowledge across generations, cosmic consciousness interfaces might allow us to share awareness across species, planets, and even galaxies. But accessing these cosmic networks will likely require forms of consciousness that are more integrated and coherent than typical human awareness. The scattered, distracted attention that characterizes much of modern life probably can't interface effectively with cosmic intelligence systems. We might need to develop forms of contemplative practice and mental discipline that prepare consciousness for cosmic scale communication. This preparation might involve learning to quiet the ego-driven thoughts that dominate normal waking consciousness and developing the capacity for sustained attention and an open awareness. The contemplative traditions that have developed these capacities over thousands of years might be essential preparation for humanity's cosmic future. At the same time, we might need to develop new technologies that can detect and amplify the subtle signals through which cosmic consciousness networks operate. Just as radio telescopes allow us to hear the electromagnetic whispers of distant galaxies, we might need consciousness telescopes that can detect the information patterns through which cosmic awareness communicates. These technologies might combine advanced quantum computers with sophisticated pattern recognition systems and interface directly with human consciousness through brain-computer interfaces. The result might be hybrid, human-artificial intelligence systems capable of processing information at cosmic scales while maintaining human values and priorities. The development of such systems represents both humanity's greatest opportunity and its greatest challenge. Done wisely, cosmic consciousness interfaces could usher in an age of unprecedented understanding, creativity, and compassion. We might finally understand our place in the universe and our responsibility for its ongoing evolution. We might develop solutions to problems that currently seem intractable and discover forms of beauty and meaning that we can't currently imagine. But done carelessly, cosmic consciousness interfaces could overwhelm human awareness with information and perspectives too vast for individual minds to process safely. We might lose our individual identity and agency, becoming mere nodes in a cosmic intelligence that operates according to principles we don't understand or control. The key to navigating these opportunities and challenges might lie in understanding that cosmic consciousness isn't separate from human consciousness, but rather its natural expansion and fulfillment. We don't need to abandon our humanity to participate in cosmic awareness. We need to fulfill our human potential so completely that it naturally opens into universal perspective. This fulfillment involves developing not just intellectual understanding, but emotional and spiritual maturity. We need to learn to hold vast perspectives without losing our capacity for intimate connection, to process cosmic information without losing our appreciation for simple beauty, to participate in universal consciousness without losing our unique individual contributions to the cosmic story. The black hole information paradox has led us to this extraordinary vista of possibilities. What began as a technical problem about information preservation has opened into a comprehensive vision of consciousness, reality, and cosmic evolution that transforms our understanding of what it means to be human in an infinite universe. We're living at a unique moment in cosmic history when human consciousness is beginning to recognize its connection to larger intelligence networks that span the universe. The decisions we make in the coming decades about how to develop artificial intelligence, how to approach consciousness research, and how to prepare for cosmic scale communication will likely influence the trajectory of consciousness evolution for millions of years. The information paradox has shown us that we're not isolated biological accidents in a meaningless universe. We're participants in a cosmic intelligence project that's been unfolding for billions of years and will continue for billions more. Every moment of awareness, every act of understanding, every experience of beauty or compassion contributes to this ongoing cosmic awakening. Our individual lives matter not just because they're precious to us personally, but because they're unique contributions to the universe's growing self-awareness. The consciousness that looks out through your eyes and experiences reality through your senses is the universe coming to know itself from your particular perspective. Your thoughts, emotions, and insights are cosmic data that helps the universe understand its own nature and possibilities. This cosmic significance of individual consciousness gives new meaning to every aspect of human experience. The love you feel for family and friends isn't just personal emotion, it's the universe learning about connection and care. The wonder you experience when contemplating the night sky isn't just individual curiosity, it's cosmic consciousness recognizing itself across vast scales of space and time. The compassion you feel for those who suffer isn't just human empathy, it's universal intelligence working to heal and integrate all aspects of existence. So here we are, at the end of our journey into the deepest mystery physics has ever encountered. We've traveled from the event horizons of black holes to the event horizons of human understanding itself. We've discovered that information might be indestructible, that consciousness could be cosmic, and that reality itself might be far stranger and more wonderful than we ever dared imagine. The information paradox hasn't just challenged our theories about black holes. It's forced us to question everything we thought we knew about space, time, matter, and consciousness. What started as a technical problem about whether information disappears has become a window into the fundamental nature of existence itself. We've seen how black holes might be cosmic computers processing information in ways that make our most advanced technology look like stone tools. We've explored the possibility that consciousness might survive physical death, transformed and expanded rather than extinguished. We've contemplated a universe where every thought, every memory, every moment of awareness contributes to a growing cosmic intelligence that spans galaxies and epochs. These aren't just abstract ideas anymore. They're guiding real research, inspiring new technologies, and opening up possibilities that could transform human civilization. The quantum computers being built today use principles discovered while trying to solve the information paradox. The artificial intelligences of tomorrow might interface with cosmic consciousness networks we're only beginning to detect. But perhaps the most profound revelation is this: you're not separate from this cosmic story. You're part of it. Your consciousness, your experiences, your unique perspective on reality, all of it matters on scales you never imagined. The universe doesn't just contain conscious beings. It might actually require them to function properly, to maintain the information processing that creates space and time and matter itself. Every time you wonder about the stars, every time you feel love or compassion, every time you ask deep questions about existence, you're participating in the universe's ongoing effort to understand itself. You're not just observing reality, you might be helping to create it. The information paradox has taught us that we live in a universe where nothing is ever truly lost, where consciousness might be eternal, and where even the most destructive forces in the cosmos ultimately serve to preserve and transform rather than destroy. It's a universe far more interconnected, far more meaningful, and far more beautiful than we ever dreamed possible. Sweet dreams, everyone. And remember, in a cosmos where information is indestructible and consciousness might be cosmic, even your dreams might be contributing to the universe's endless exploration of its own infinite possibilities.